Welcome to the wonderful world of physics. This is Physics 102A, the homework solutions for Chapter 1. We start with number 9, a multiple choice question. It says 10 million kilograms can be written as which of the following numbers of grams? So we'll start with the given information. So 10 to the 7th, that's 10 million kilograms. Put it over 1. And then we'll use the conversion that 1 kilogram is 10 to the 3rd grams. So we put 1 kilogram in the denominator so that it'll divide out with the kilograms in the numerator here. And 10 to the 3rd grams, so you see this fraction here is the equivalence. 10 to the 3rd grams is equal to 1 kilogram. Then the kilograms will divide out, and up top it'll leave the units of grams. We've got 10 to the 7th times 10 to the 3rd, and that gives 10 to the 10th grams. And in the book, that is multiple choice answer B. Number 11, the age of the universe is approximately 13.7 gigayears. This is approximately how many seconds? And again, multiple choice. We'll start with the given information, 13.7 gigayears, put it over 1. We recognize that giga means 10 to the 9th. So we'll say 10 to the 9th years over 1 gigayear. That'll make the gigayears go away. And then we're left with, we have it in years now. We need to get this in seconds. Now, if we want to be precise, we could calculate how many seconds are in a year. You could take 365, it's actually because of leap years, 365.25 days in a year, times 24 hours in a day, 3,600 seconds in an hour, and we could multiply all that out. However, in the conversions in the front flap of the book, it tells you in the front flap of the book that a year is 3.16 times 10 to the 7th seconds, and you could use that. What I've done here is an approximation because the multiple choice question asks for approximately, and you can look at the choices and see that they are so diverse from each other. They all have a coefficient of 4.3. It's just a matter of what power of 10. So whether we use 3.16 times 10 to the 7th or pi, which is 3.14159 times 10 to the 7th, or calculate it out more precisely, it's not going to throw us off that much. So I've just used pi times 10 to the 7th seconds. It's about how many seconds are in a year. And we get the answer of 4.3 times 10 to the 17th seconds. Number 13, a car is speeding down the road at 85 miles per hour. In SI units, that's System International units, this is how many meters per second. So I'll do 85 miles per hour. I'll convert from miles to meters by doing 1609 meters over 1 mile. Look at how the miles divide out, leaving us with meters. We take care of these hours in the denominator by multiplying by 1 hour, which is equivalent to 3,600 seconds. The hours will divide out. And we multiply and divide through, and we get 38 meters per second. Answer A. Number 18, expressed with the correct number of significant figures, what is the volume of a rectangular room that measures 12.503 meters by 10.60 meters by 9.5 meters? And all of those answers given give the correct value, but the question is more about significant figures. So we look at what information went into this problem. We're multiplying those 3 quantities. This first one has 5 significant figures. The second one has 4 significant figures. And the third one has 2 significant figures. So the number of significant figures in our answer is going to be limited to the least accurate number that was given, and that's the one with 2 significant figures. So when we multiply them, we get something like 1,259 cubic meters, but we're going to round that to 2 significant figures. So we get the 1, and something's going to happen to the 2. We see because it's followed by a 5, it's going to round up, so that becomes 1,300 cubic meters. Number 19, a 4-part problem, express the following in scientific notation. And so we get 13,950 and we're going to make it 1.395 times 10 to the fourth. So you move the decimal point over 4 spaces, and it's times 4 powers of 10. The next one, 0.0000246 kilograms. And so you move the decimal point over as many places as will get it right after the 2, and that is 5 places. And since in moving the decimal point over, we multiplied by 5 powers of 10, we need to balance that out by multiplying by 10 to the negative 5. So it's going to be 2.46 times 10 to the negative 5. The next one is a point, and it sure helps in the textbook that they space out in groups of 3 those zeros. So you have a string of zeros, then 3, 4, 9, and we need to move the decimal point over 3, 6, 7, 8 spaces to get it after the 3. So we have 3.49 times 10 to the negative 8 seconds. Remember that for proper scientific notation, the coefficient will always be something greater than 1, or at least 1, I should say, and less than 10. And finally, the last one, it says 1,280,000,000. And so we're going to move the decimal point to the left 9 spaces, effectively dividing by 9 powers of 10. And we'll balance that out by multiplying by 10 to the 9th. So we have 1.28 times 10 to the 9th seconds. Number 23, Earth's mean radius is 6.371 megameters. Assuming a uniform sphere, what is Earth's volume? And using the given mass, compute Earth's average density. And how does that compare with 1,000 kilograms per meter cubed, the density of water? All right, so there's the radius. We're going to use the formula for volume of a sphere. Volume equals 4/3 pi r cubed. And notice that we need to get it all in meters. We need MKS units. So the 6.371 megameters, let's turn that mega into times 10 to the 6 meters. You should get a volume for the Earth of 1.083 times 10 to the 21st cubic meters. Density is the mass that's given divided by the volume, and it ends up at 5511 kilograms per cubic meter. Then we compare that with water, and we see, yes, the planet Earth is more dense than water. Number 27, a cheetah runs at 70 miles per hour. Express this in meters per second. And this is very much like problem number 13. It's the same conversion, miles per hour to meters per second. So just as I did in problem 13, here's the conversion. We do 1 mile is 1609 meters, 1 hour is 3600 seconds. We line them up in such a way that the units divide out the way we want them to, so we're left with meters per second. And 2 significant figures is appropriate here, and so we'll say 31 meters per second. Number 31, one place in the Hoh rainforest in the state of Washington receives an average annual rainfall of 200 inches. What is this in meters? And if you go to the front flap of the book, it gives inches to centimeters, not specifically inches to meters, but we can deal with that. We'll start with the given information, 200 inches over 1. We'll convert, recognizing that 1 inch is 2.54 centimeters. That'll give us centimeters, but we want this in meters. So a centimeter is 10 to the negative 2 meters. The units all divide out except for meters, which is what we want, and we get 5.08 meters. Number 39, Earth's equatorial radius is 6378 kilometers. And that's a lot like, if you go up to number 23, it says Earth's mean radius is 6.371 megameters, which is 6371 kilometers. So now it's giving the equatorial radius, 6378 kilometers. A spacecraft is in circular orbit 100 kilometers above the equator. If the spacecraft orbits every 86.5 minutes, what is its speed? All right. Now, we have to think the spacecraft is going in a circle. And what is the radius of its circle? Well, it's 100 kilometers greater than the Earth's radius. And if the Earth's radius is 6378 kilometers, then that means that this spacecraft is going in a circle of radius 100 plus that, so 6478 kilometers. From that, we do speed is distance divided by time. The distance it goes in one circular orbit is 2 pi times the radius. That's the circumference of a circle. The time is given for one complete orbit, 86.5 minutes. So if we plug those values in, 2 pi times 6478 kilometers, divide by 86.5 minutes, we get an answer that you see below. But it's in kilometers per minute, so we get 470.5488 kilometers per minute. Let's get that in proper MKS units. So we want to turn those kilometers into meters and those minutes into seconds. So let's get rid of the kilometers first. 10 to the third meters over 1 kilometer. Now let's get rid of the minutes, 1 minute over 60 seconds, and we get 7842 meters per second. Number 44, what are the dimensions of density? What are the SI units of density? So the dimensions, and we've seen this came up in the book, and also it came up in a previous homework problem involving Earth's density, problem number 23. You calculated Earth's density by doing mass divided by volume. It even gave in problem 23 the SI units for water. It said kilograms per cubic meter is the density. So problem number 23, it was already answered for us, the units anyway, kilograms per cubic meter. But now let's think about the dimensions. Remember, the three main dimensions are mass, length, and time. So if density is mass over volume, we think volume is length cubed, so the dimensions are mass over length cubed. And from there we assign the appropriate units. Mass is kilograms, length cubed would be meters cubed, and so there are the units. Number 53. Find the area of a right triangle with sides 15 centimeters, 20 centimeters, and 25 centimeters. All of those are given in 3 significant figures. Express your answer with the correct number of significant figures. All right, I've drawn the picture there. 15 by 20, the hypotenuse is going to give 25. We know it has a hypotenuse because it says it's a right triangle, and the hypotenuse is always going to be the longest side. And so with that in mind, we have the area of the triangle, 1/2 base times height. So 1/2, you can do 15 times 20 or 20 times 15, doesn't matter. But you get 150 when you multiply that, square centimeters. And then proper significant figures, well, that puts it, we are given 3 significant figures for those values. And so we could say 150, and we could put an underline under the 0. Or we could use scientific notation to express 3 significant figures. So we can write it as 1.50 times 10 to the second power square centimeters. Finally, number 57 is an estimation problem. Estimate the number of heartbeats in an average lifetime. All right, so this is going to be a rough estimation. But we think an average lifetime, we want to think about how often the heart beats. And I know there's a diversity of people with different heartbeats, and certainly as we age, our heart rate changes. And even through the course of the day, with different activities, we have higher and lower heart rate. When we're at rest, our heart rate might be lower. When we're actively working, if we're doing aerobic exercise, it might be more than twice as high as our rest rate. Different people have different normal heartbeats. So some people some adults might have a typical heart rate of maybe 70 beats per minute. Someone who's more athletic and into aerobic exercise might have a resting heartbeat of 40 beats per minute. But so that's why this is an estimation problem. Roughly, for the average human life span, how many heartbeats? So I'm going to go with average human lifespan. I know this, generally speaking, is increasing as the years go on, but one figure I looked up for humans across the world, maybe about 70 years. I just did 72 years. Whether it's 70 or 72 or 75 isn't going to make a difference compared to the imprecision of how many beats per second I'm estimating. So we'll just start with the number 72 years as an average lifespan. And we think about, well, how many seconds is that? Let's multiply by pi times 10 to the seconds over years. Again, it's more accurately 3.155, I think, times 10 to the 7th, but that's only going to be off at the third significant figure. Now we have how many seconds. Now we need to think how many beats per second. Well, as a rough estimate, let's say about 60 beats per minute, which is about 1 beat per second. And so if you multiply those out, you get roughly 2 billion heartbeats in an average lifetime. That is the end of the Chapter 1 homework. Have a great day.